Welcome to Walk About the Galaxy, the astronomy podcast where the science is universal, the opinions are personal, and at least some of the content is astronomical. We are Strange Charm atop the Astroquarks, also known as Josh Caldwell,
Addie Dove,
and Jim Cooney.
Coming to you from physically but not socially separated locations near the University of Central Florida. Remember to check out our website to see how to get our snazzy shirts and subscribe to us on all platforms, including YouTube, where you can catch our first and soon-to-be Grammy-winning music video, the Astroquarks song. Post your prediction for orbital launches in 2021 on one of our social media thingies with hashtag AskWTG for a chance to win up to 2 of the following 3 prizes. A brand new electric car, a Walkabout t-shirt, and a Walkabout sticker. Our stumpers today are very physicsy.
Ooh.
Challenging.
Neither of you seems to be particularly. I guess it's because
I'm
you're
excited. I love physics.
No,
What?
I mean about the prizes, but I guess because you're co-host, you're ineligible for,
Yeah,
for
I
the
can't wait.
electric car.
To be, you will note we didn't say anything about the scale of the electric car.
That's true.
That is true. That is true.
I think even a scale electric car is outside of our budget. So,
any functioning electric car.
yes.
Yes. So our stumpers today are physicsy. You know, every now and then, why not?
Why not?
So
Why not?
and they're physicsy, and therefore they're also astrophysicsy, or can be, but not exclusively. Anyway, I'll shut up. Jim, Kelvin Helmholtz instability. You may have had this one even before, but for our new listeners, Kelvin Helmholtz instability or Rayleigh Taylor instability.
Instabilities. Definitely.
We know a lot about those.
I've had instability on my mind lately. I don't know why.
It's weird. That's weird. Yeah. The what was the second one? Rayleigh Taylor.
Yeah.
That's my favorite instability.
Is it? Why is that? Is your favorite of those two, or it's your favorite of all instabilities?
I think it's my favorite of every instability that I can think of.
Okay,
I don't know if I can name any other instabilities. There's one more that I could think of, but there are many. But the Rayleigh Taylor one is awesome because it involves some cool things, or it has applications to some cool things like supernovas.
Yes.
And like mushroom clouds from atom bombs and things like that. So it's pretty cool. This is an instability, of course, is like try to balance your pencil on its tip. Right? You could do it if you do it absolutely perfectly, but any little air whiff or something like that will knock it over. And once it starts,
can't you do that like during the equinox or something?
That's right. Balance an egg on its side, or whatever. But yeah, so an instability just means it's like an unstable equilibrium, right?
Right.
You can do that. And anyway, so for example, you could balance a drop of oil on top of water, even though oil is denser than water. Would usually the other way around.
The other way around.
Other way around. A drop of water on top of oil, because water usually it would go to the bottom. But if you perfectly balance it on top, it would stay on top, except if any little thing goes wrong, then the whole thing goes down, and then it devolves into this chaotic thing as it's going down. And that's it's when a denser thing or a less dense thing is accelerating into a more dense thing.
Right. And so what's the supernova application then?
Yeah, because then in a supernova, you get this extremely hot gas that is underdense, so less dense, plowing into denser, cooler gas around it, and so you get all these weird effects.
It happens in my house sometimes.
Gas goes into the higher dense gas, and you get these beautiful patterns and crazy things that go on. Those supernova remnants have all these cool
tendrily type things.
Yeah, exactly.
Yeah,
that's because of that stuff. It's pretty cool.
My fluid physics teacher in graduate school, Yuri Tumre,
I've heard that name.
Explained the Rayleigh Taylor instability to us. He said, imagine taking like a sheet of water 1 inch thick and putting it up on the ceiling, and it's perfectly flat and it's up there on the ceiling, and with no perturbations or anything like that, it's going to either be balanced up there, or if the air can move, it would fall. But of course, the tiniest little wrinkle in the surface of the water causes a finger to come down, which then accelerates. And so you get all these sort of accelerating multi-scale tendrily things. So I always, when I see a supernova or Rayleigh Taylor instability, I always think of that analogy, and
So
a
when you see,
freaky nightmarish image of my ceiling covered with water.
I was gonna say, so when you have water leaks in your house, you also think of supernovae?
Yeah.
That's right. I'm like, the star exploded.
Do not try this demonstration at home.
Okay. Well, Addie,
Yes.
also physicsy, your is instead of instabilities, but it's also something sort of undulating. It's waves, electromagnetic waves, our
Okay.
old friends, or quantum mechanical waves.
Ooh.
I'm gonna go with EM waves because I understand them better, even though they're
I'm with
super
you.
complicated and I don't understand them that well. I mean, but quantum waves, complicated.
Yeah.
So yeah, EM waves are light. I like light. Like I like to see things and detect things.
I've been thinking,
Quantum, you're like, I don't know, maybe it's there, maybe it's not.
yeah, the
Is the
whole
quantum
quantum
mechanical
wave.
wave even a real thing? I don't know.
That's the other
Well,
thing.
yeah. I was
Yes and
looking
no.
I was trying to figure out how to like put quantum wave function in here as a way of like, can I even say quantum mechanical wave?
You
We're
did.
going with
Then in a meaningful way. I've been thinking a lot about electromagnetic waves.
gravitational wave.
I thought about doing that one, but I was like, I'm gonna make it a little bit tougher.
Okay.
I've been thinking about EM waves a lot recently because, as you know, and we'll be talking
As
about
one
this in
does.
a little bit, we have a satellite that we will soon be trying to communicate with via electromagnetic waves.
Ooh.
Very exciting. Well, today we'll talk about that. Also, something called Bumblebee Gravity, very, very, very old rocky planets, and many other exciting new spacecraft developments for 2021. But first, this episode of Walkabout the Galaxy is brought to you by dogs. What? What did you say? Did you say go for a walk? Go for a walk about the galaxy? Yes, yes, yes. I want to go for a walkabout. I want to go for a walkabout. Yes, yes, yes. I'm happy. I'm so happy. I love you. Let's go on a walkabout together. I'm ready. Let's go. Open the door. 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 I'm ready. Open the door. Open the door. Walk about the galaxy. Let's go for a walk about the galaxy. I'm so happy. Open the door. Here we go. Dogs. Share moments. Share life.
I will note that we're recording this on a Catterday, but we'll allow dogs to
What's a
sponsor us on the
Catterday?
pod.
What's
It's
a
a different word
Catterday?
for Saturday.
Oh,
All Saturdays are now cat themed. Okay.
Mhm.
I don't know what that thing was. Maybe it's like a
What was it?
company or
share
something.
moments. Share life.
Oh.
Polaroid
You sh- oh, very
Oh.
good. Very good.
or like Canon.
Very
Kodak.
smart.
But I give you,
Ah,
a 99 out of 100 for that guess,
Yeah,
because that
yeah,
was,
thanks.
yeah,
That's
figure,
nice.
Kodak.
Yeah.
Interesting.
yeah. So we have our own space news coming up, which is the upcoming launch
In a week full of
of,
space news, we're going to
there's,
hopefully cap it off.
yeah. So there's a new small orbital launch vehicle called Launcher One, which is a Virgin Orbit launch vehicle, air launched. And their second test flight is scheduled for tomorrow as we're recording it, which means hopefully it will have happened by the time you're listening to this show. And it's carrying about 10 Cubesats into orbit, one of which was built by us here at University of Central Florida. I say by us, of course, I was mainly sort of peering over people's shoulders, not actually building things.
Mostly
But
students.
I made some decisions and
But that's
wrote the
cool. So
proposal.
a lot of people, got that chance to work on that, right? You got a bunch of graduate and
Yeah.
undergraduate students who got to say they worked on a thing that's going to be in space soon.
Yeah.
Yes,
Yeah.
mostly undergraduate students. So
Yeah.
so
I soldered a
Addie,
couple things, I think, on that one.
Nice.
did you? Nice. All right,
I think
excellent.
so.
Yeah. So it's been a long road because we had delays in the development of the satellite, which fortunately coincided with delays of the launch vehicle, and everything came together beautifully. And so that's going up. It's called QPACE, and it's going into space tomorrow. It stands for CubeSat Particle Aggregation and Collision Experiment. And It's a fun little experiment. So
It
hopefully we'll
is.
be able to share the progress of that with you as we go. Um,
And you mentioned
it,
electromagnetic waves, the way we communicate with it. So it goes into space and then it has its own little radio on board. And so we communicate with it, hopefully with our ground station.
its
And
antenna is a guitar string.
yeah.
So
Uh,
how much
I think
power does that thing?
I think it's an E, maybe. I forget which note
Oh,
it
which
is, but I
string?
think it's
I
an
think
E
it is an
guitar
E.
string.
Yes.
Yeah.
So is this run off like a 9-volt battery or something? Like it can't, it's a tiny little
Yes, Jim.
satellite, so it can't
Yep.
It
it
does
can't
have
use too much power.
it has lithium ion battery packs, or yeah, and they charge via solar panels that are on the external sides of the CubeSat. Um, and we've done a lot of testing of the batteries in vacuum, running them and charging them and things like that. Yeah. And but like the radio is actually one of the things that takes up the most energy. Like
Right.
being able to power that and do communications is what takes up the most energy on these things.
Right.
Yeah. So, and we'll
Yeah.
be listening
And
to it from here at UCF as well, from
it's going to join its sister satellite in orbit,
SurfSat.
SurfSat. SurfSat is in orbit. We unfortunately did not figure out the EM wave thing for it.
But we may yet.
So we may yet.
Yeah.
So we'll see.
So today there was a major milestone test that was live streamed by NASA of the core segment of the Space Launch System. This is the new heavy lift vehicle that NASA is developing to carry the Orion capsule to carry humans beyond low Earth orbit. So NASA is now contracting with SpaceX and I guess it's ULA and Boeing to have astronauts go to and from the International Space Station, but this would be for like exploration missions and eventually going to the moon. So the Orion capsule is a little gumdrop, human spaceflight capsule, and the SLS is like sort of like a stretch shuttle without the shuttle.
Yeah.
So the core section is just a big solid rocket thing with 4 engines at the bottom, and then they slap 2 Mongo solid rocket boosters on the side of it, which actually provide most of the thrust. But today they were doing it. Well, it's supposed to be an 8-minute test of the core. Bolt the thing down, turn on the engines, and let her rip.
And they did about an eighth of the test.
Unfortunately, it terminated. This is just a couple hours ago as we're recording. It terminated about a 1 minute into the test, so we still don't know what's going on with that. But we'll post information on that. But there was a successful private launch of a different type a few days ago, having to do with human spaceflight.
There was.
I'm looking at Addie to talk about that one because you're.
It was the first launch of the crew capsule from Blue Origin. So this is a New Shepard launch. So the same type of booster and capsule that they've flown for like our payloads, for instance. But this one is a new capsule and it was a new booster as well. And so those both flew, and this is again a suborbital vehicle. So this is for space tourism for the capsule. So it goes up, separates. They talked about on the thing this time how once it's up at sort of the highest altitude, they spin it very slowly so that all of the people on board will get different views. They have giant windows in these things, so you can have really good view.
Largest windows in space, they like to advertise.
Yeah.
And so this capsule, I mean, the sort of basic design is what has flown before, but these are new sort of serial numbers. And this capsule was like fully decked out for people. And they had they had Mannequin Skywalker. Going for a ride, but it's like, looks ready for people. And this was the 14th flight of this rocket configuration, first of these particular units, as you mentioned. But I think 2021 is going to see people going up into space on that vehicle. And I'm even going to say more than once.
Ooh. You guys got your tickets yet?
Yeah.
Well, they haven't started selling them.
They haven't?
They haven't.
No.
Okay.
Yeah, so they have a very different model than Virgin. It's interesting.
Yeah.
They haven't even like ever said anything even close to like what the cost might be either.
What would you guess?
I mean, it's going to be similar to Virgin, I think.
Which is what, like a few $100,000 or something?
Yeah.
We have no
Chump change.
idea, but yeah, Virgin's charging somewhere in that range based on what they charge for payloads, which take up the fraction of the space of a person.
Yeah.
Yeah, it'll be six figures. I don't know what the first digit's going to be though. That's my guess. Anyway.
All right.
Anyway, there was also another bit of sad space news, Addie. Do you have any insight into that one?
Oh, good transition there. No, I don't have any particular insight, except that the mole they've decided to officially stop trying to dig with the mole,
Which
the InSight mole on Mars.
We've been giving updates on this sort of periodically for what seems like a very long time.
Yeah.
And
There's a little bit, at first it was very exciting when I got there, and then it was like, oh no, and then there was some progress, and then backwards, and then some progress again. But it turns out just like it can't dig in the soil that they're in. And it's like got very different properties than other places. They've done little dig tests before, I guess, on Mars. And I guess they didn't test it in a very wide range of simulants. And so they weren't predicting sort of the cohesive nature or the lack of cohesive nature of the soil they're in.
Yeah, and so it's just there's nothing for this thing to push against somehow. It just can't get a grip on the dirt to push itself down in.
Yeah.
So no more
It's like
digging
when you're
for the
trying to
Mars
pull
InSight.
yourself on an ice rink or something, and you like
That's
can't.
right. Yeah.
You just keep trying, but you don't get. I don't know. That's a bad analogy.
Actually,
I'll come up with a better analogy.
And I don't think we've ever been ice skating together, Addie, but that is exactly what it's like when I am ice skating. It is a stationary man flailing about, moving all four limbs to absolutely zero effect.
There you go. Beautiful physics experiment. Yeah.
Yes. Yeah.
So Josh on an ice skating rink is to the mole.
Right. Josh to ice skating rinks is as the mole is to Martian dirt.
Yeah, it's really unfortunate because that was like a third of the science plan for InSight, right? Was this heat probe that was going to dig down in. So they've extended the mission a little bit for the seismometer. So they're going to keep doing some cool measurements with that. But yeah.
I'll mention one bit of Earth news as we're kicking off 2021. 2020 essentially tied 2016 as the hottest year on record. Oh, I wasn't going to talk about the Cleveland Browns, Jim. Sorry.
Oh.
Yeah, sorry.
Yeah. This is very exciting Earth news. I've been a Cleveland Browns fan since I was, 5 years old, and it was about then that they last went to the playoffs and won a playoff game. So tomorrow, as we record this, they're playing the Chiefs.
Was that pre-industrial revolution when the Earth was cooler?
Yes.
To tie the two statements together.
Roughly the same time. Yeah, so I apologize. I got Browns there. You said something about what we did. What we tied the hottest temperature. What
it was as hot as 2016, which was the previous hottest year, which was an El Nino year, which is a natural oscillation in surface temperatures. So that year was particularly hot. Now we're back up to that level in a La Nina year, which is a cooler than normal year in that cycle, but due to the overall global warming. And atmospheric CO2 is now 50% higher than it was in pre-industrial times. Speaking of pre-industrial times.
Yikes.
50% increase.
This is not good.
It's
been cool here in Central Florida for the last few weeks, so therefore global warming is not real.
I see.
Good point.
Yeah,
I was reading about so there was stuff at the beginning of the pandemic when people just stopped driving, right? About how it was changing some of the emissions and things like that. And so like overall emissions have decreased, and like that's probably a net good thing. But it turns out that like locally, some of the emissions like help reflect heat, right? So it actually made it worse in some places locally. So long term better, short term problematic.
Also, it seems like the emissions level have now almost 100% rebounded to what they were pre-pandemic. Yeah.
Really?
Yeah.
Even in places like LA? I doubt that.
Not. I mean, I'm talking globally.
Yeah.
So yeah. Definitely, it's not there yet. But well, let's move out beyond the Earth to the outer realms. So I'm just so intrigued by this Bumblebee Gravity thing.
Yeah.
Is it related to Transformers?
It is not that bumblebee. But it's related to the actual insect, the bumblebee, in
Oh.
some very tangential way.
Yeah.
Extremely tangential way. But this was just was brought to our attention as a neat. I mean, we're always trying to think of new grand theories, because, as we've said many times, our big theory of gravity, the general theory of relativity, doesn't work with quantum physics, and so we're always trying to figure out what's the deal. And so people are mess around all the time.
What's the deal?
What's the deal? What's up? So alternate theories of gravity are very popular things to try and maybe one of those things can mix well with quantum physics or something like that. So there's this cool set of kind of alternate theories of gravity called Bumblebee Gravity. The name, well, we'll talk about the name in a second, but basically, in these theories of gravity, let's see, how do we even talk about this? It turns out it's very complicated.
That's what we do here, Jim.
There are these complicated things. It's all about symmetry, right? And so Josh was very excited. We were talking before the show about symmetry, and we get a chance to talk about symmetry and physics and so forth, because it turns out that if you express the fundamental laws of physics in terms of symmetries and conservation laws, there's these beautiful connections between the two. So that it turns out that if you posit that physics is the same no matter where you do it, right? So that is, if you do physics here or do physics there, doesn't matter. Translational symmetry. Yeah, you do physics here, but you could do physics there, and you get the same results, right?
That sounds like a Dr. Seuss book.
Yeah, physics here, physics there, physics everywhere.
You should make a walkabout Dr. Seuss book.
I could collide these particles in a box. I could collide them with a fox.
There you go.
I can collide them here. I can collide them everywhere.
I could collide them up a tree. I could collide them under the sea.
And you should get the same result anywhere. And that fact leads to the conservation of momentum. It turns out that it's seemingly totally unrelated law in physics, right, is related to the fact that you can do the physics is the same everywhere. And the fact that you can do physics experiments now and 10 minutes from now and they should give you the same result gives you conservation of energy, it turns out.
So that's just super cool, because when we teach introductory physics, I have never really cast it in that way.
Certainly not.
Right. We're taught, we in the intro physics, especially if we're teaching intro physics for non-physics majors, we're like, there's this thing called momentum, and it has to do with a mass and a velocity. And then when these things run into, it's all about collisions of things and whatever. Mm-hmm. But it follows naturally from a very simple idea about there's no special place in the universe, which is just super cool.
It is really beautiful, yeah, and it's unfortunate that you can't really get at that in a physics 1 class. These things are really beautiful, but they require a little bit of mathematics or whatever to really get at them, to really see where they come from.
Mathematics or whatever,
some kind of thing.
Something.
But it turns out if you take a symmetry like translational symmetry, the symmetry you're just talking about, there's a more general symmetry out there that we're pretty darn sure is a symmetry of nature. It's called Lorentz Symmetry. And this is the symmetry that Einstein's special theory of relativity is based on. That is, you should be able to move wherever you want. You should be able to rotate however you want, right? So if I rotate myself 90 degrees, that shouldn't change the nature of physics, right? And if I'm doing my experiments in a laboratory that's moving, right? If I'm moving at a nice uniform velocity, I should be able to do my physics experiments and I should get the same result. Those 3 things put together, that's called Lorentz Symmetry. You should be able to do any of those things and end up with the same results. And we are so sure that that's right, because the universe just doesn't make sense if it's not. But what if it's not? And that's what the Bumblebee gravity things are all about. They're like, what if it's not? What if the universe is not symmetric in that way?
Right. But also, isn't it sort of like these things with some of the other things we've talked about before with like modified Newtonian dynamics or whatever, where they're like, well, it's like that almost, it's only not like that in very certain special conditions.
Yeah.
Is that right? Or, I mean, obviously we know it's mostly right most of the time because these things are experimentally tested and verified.
Right. Right, and so you have to find a circumstance in which you could experimentally verify this, right? That's the hard part about this. Is you're right, absolutely right. It's obviously approximately true because every experiment we've ever done, it's true for, right?
Works,
These
right.
symmetries are true, so it must be approximately true, but maybe it's not absolutely true. And if it's not absolutely true, that's weird actually, because that actually does mean that if you rotate yourself 90 degrees, physics is a little bit different.
I'm
Which so
pretty
there's
sure that's true because I have a hard time reproducing results of some of my experiments.
oh yeah yeah.
Oh,
That's
this will
definitely
be a
not your
great new.
experiment's
This will be.
problem. Yeah, that's
This is now
fundamental
the great.
physics.
This is the new excuse for every failed physics student's project.
Bumblebee
Like,
Gravity.
I swear I did the project right, but I think it had something to do with which way the table was oriented or something. Because like it,
Yeah.
Mhm.
which way was it supposed to be oriented?
Um, but the cool thing about this is in these theories of gravity where one direction is a little bit different than the other direction, it kind of accelerated expansion of the universe naturally falls out of that. It's not immediately obvious at all how that falls out of that, but it does. So dark energy basically falls naturally out of that, which is nice because we have a hard time explaining why you'd have dark energy in the first place. And if these theories of gravity are right, then you'd have this. Um,
I don't want dark energy falling out of stuff.
no.
Dangerous.
Well,
Oops.
you did a pretty good job explaining it, Jim. But I think if I read the first sentence of the paper, this will really make it clear.
All right, go.
Okay. In this work, we present black hole solutions with a cosmological constant in the Bumblebee gravity, which provides a mechanism for the Lorentz symmetry violation by assuming a non-zero vacuum expectation value for the Bumblebee field.
Yeah,
And I just
Obviously.
love that because it talks about the Bumblebee field.
the Bumblebee
Yeah.
field. So
Field
we
of
So
bumblebees.
should say something about why it's called Bumblebee. Uh,
So it's
there's a story that
yeah.
physicists, when they first really took a close look at bumblebees and bumblebee wings, did
How do
some
they work?
and concluded that bumblebees cannot fly because their wings are apparently incapable of producing the lift that you need to.
They're fat little dudes. How are they going to fly with those little wings?
No, I mean they said this theoretically impossible that a bumblebee can fly, and yet they flew. So even though we claim that it's theoretically impossible to violate Lorentz symmetry, maybe you do, right? And that's the idea. That's why they named it that. I don't know if that's a great reason to name it that, but
Bumblebee
they
fields. Well, but
Bumblebee.
the idea for this particular paper, just to wrap this up, is that you were talking about like, okay, can we find a test or
We
something?
find a
Is
test.
there
So you
some
sort
sort of
of
prediction
right. So you're going to
that
find a test in places where gravity is extreme, because that's where the places where the this would diverge the most from our standard theories, and that's near a black hole. And so the calculation of this paper was claiming that the size of the shadow of the black hole, remember that those images from M87 star of the shadow of the black hole, the size of that shadow will be slightly different in this new kind of in bumblebee gravity than it is in regular general relativity. Unfortunately, our actual measurements of that shadow are not precise enough to rule one or the other out. I think they're supposed to be about 10% different from one another, and
yeah.
those images are pretty fuzzy right now. But maybe with a few generations improvement in the technology, we can actually use that to tell the difference. And so that's nice because it's not just some random theory that somebody's come up with that you can't possibly test. It's a testable thing
String
with
theory.
with yeah, exactly.
I-
Excuse
If
me.
It's a
we
testable thing.
if we put a bunch of telescopes or some telescopes on the moon to combine them with the Earth telescopes, will that help us get much better
Absolutely.
black hole pictures?
Yeah, because then you have an effective telescope the size of the distance between the Earth and Moon. That's going to be friggin' amazing.
Which is a lot bigger than the size of the Earth.
Turns out.
By about
Turns
yeah,
out.
yeah. Cool. All right. So, well, we won't have an answer to the Bumblebee field soon,
No. But maybe
but
in 60, 70 years.
60 or 70 years. Oh, come on, man.
Maybe earlier. I don't know. Depends on how much money gravitational wave research gets.
Oh,
Oh.
okay. All right. Well, I'm
Well,
going to
there's
bring
all
it.
sorts of new science going to be happening now. So in the U.S., so maybe they'll get some
Oh,
good
potentially.
funding.
Yeah.
Yeah.
Well,
Did you
I'm going to.
see? Did you see? Speaking, this is relevant. That the Biden transition team just named their new science advisory team, and they elevated the science advisor to the cabinet level. am
Yeah,
the
this is
Office of
really
Science and Technology Policy person to the cabinet level.
this is really
And
fantastic.
one of the science advisory team members, the co-chair, is Maria Zuber, who is a planetary scientist.
Woohoo!
Awesome. I had
Yeah.
not seen that last bit. I was kind of wondering where my phone call was, but
Yeah.
Right.
anyway,
She
yeah.
answered the phone more
Faster.
quickly. You thought
Quacker.
it was a quacker. You thought it was
Quacker.
spam. It got
Yeah,
blocked.
that's right. Well, I'm going to bring it way back from the Bumblebee Field for your trivia to what we were talking about earlier with some of the space news. It's Jim's favorite trivia topic, and
Space
one one that we have visited before, but in honor of the launch tomorrow of our little CubeSat, QPACE, I had to make trivia about CubeSats. So guess what, though, Jim?
What?
It's multi-parts.
Oh,
What?
sweet. So I can get multiple parts wrong. Very good.
So,
No, I'll allow it this time because it is very exciting that you guys' thing is launching. So
okay.
I'll take it.
All right. Well, the first question is, as of January 1st, 2021, a couple weeks ago from when we're recording this, very simple. How many CubeSats have been launched? So just as a reminder for everybody, CubeSat is a standardized form factor that was established about 25 years ago of a cube which is 10 centimeters on a side, which is about 4 inches on a side, bigger than a Rubik's Cube and smaller than a bread box. I don't know. Anyway, it's 4 inches on a side, and that's called a 1U CubeSat. And you can actually make a satellite that size. And then
Sort of like a tissue box.
It's a smaller
single
than a tissue
box.
box. Yeah. And then you can stack two of those together. That would be a 2U. So it'd be a single spacecraft that would be 10 centimeters by 10 centimeters by 20 centimeters, or 4 inches by 4 inches by 8 inches. And Addie's CubeSat SurfSat is a 2U. And then QPACE, which is launching tomorrow, is a 3U. So it's about 12 inches long, or a little bit longer because there's this extra space in between the U's, and 4 inches on a side. So it's about a foot long. It's like the big, tall thermos size spacecraft. And inside there's the power, there's the radio, there's the computer, there's the experiment, and all that stuff. So that's what CubeSats are. They're not necessarily cubical in shape, but they're based on these units like Minecraft satellites, sort of. So as of January 1st, 2021, how many CubeSats have been launched worldwide? It's multiple choice. I decided to give you multiple choice.
Launched or successfully launched?
Not necessarily successfully launched.
Okay, launched.
Your choices are 1,357, 1,808, 2,293, or 2,611. I'll give you those numbers again when I'm asking you to guess your answers. The follow-on questions are going to be, which year saw the most CubeSats launched, and how many are currently operational in orbit?
If this was like a year ago, I would have all these numbers on the top of my head because I gave a bunch of presentations.
I know. Yeah, you gave all these CubeSat talks, right?
They are no longer in my head.
Also, they've been updated by a year because
yeah.
So
are we counting Addie's SurfSat as operational, even though it can't talk to us?
I don't know because I didn't compile the data for this.
Okay.
So
Probably
I didn't individually go through and look up all the CubeSats to determine whether they're operational.
Still look up at night when I get my little notification that it might be going over.
Oh,
you can't see it, but
no.
So now that we're sort of back from the heady realm of the Bumblebee Field, there was another interesting story about exoplanets, another one of our favorite topics, and the TESS satellite, the Transiting Exoplanet Survey Satellite, which is a kind of a follow-on to the Kepler mission, but it operates in a very different way, had an interesting discovery about an exoplanet that was a little bit surprising. How do you want to?
Sure, yeah. It's surprising because it's very small and it orbits very close to its star. It's probably sort of an Earth-like planet, in that similar size to Earth. But I think it's like 50% larger or something. But it orbits in less than half a day. So very, very close in. It's gonna be pretty toasty on that planet. And the sort of more remarkable thing about it, because we've seen a decent number of those at this point, is that it is around a very old star. So it's a small hot planet around a very old star.
So
Yeah.
old meaning what? So our sun is about 4.5 billion years old.
Hmm.
This one is how old?
Older than that.
10 plus or minus 3. So there's a big error bar there.
Okay.
Yeah.
Um, but
It's
chemic
part of the galactic thick disk. So it's a star that's in the galactic thick disk. And it's from an old population of stars that's in that
So that would mean
region.
less less
so
heavy elements.
right. So
Yeah.
remember, astronomers have this funny thing. They have two funny things related to this. One is the numbering of what they call stellar populations,
Yeah.
where the sun is a population 1 star,
Uh-huh.
and that's younger than a population 2 star. Do I have that right?
Yeah.
And so the oldest star, the sort of first generation of stars after the Big Bang, you only have basically light elements. So your original stars are not polluted with things besides hydrogen and helium,
They
but
don't
then
have any
they're
metals.
fusing and they're making those heavy elements. And that's the thing that, right, that's the second funny astronomy thing about for the story is that astronomers call everything other than hydrogen and helium a metal.
Yep.
Silly.
They're very
Oxygen,
But yeah,
sand,
those very first
everything.
all those
population of
metals.
stars, which are population 3, shouldn't have any planets at all, right? Because they don't have you don't have anything to make a planet out of.
Yeah.
Although it's certainly possible that one of those stars would have planet that it had captured or something like that in some freak
Hmm.
event, but that's probably not what's happening here. And this isn't a population 3 star, right? This is a population
Population
2,
2
two.
star.
Two
right.
star.
But it's what the astronomers call Metalpoor. So it's the most metal-poor planetary system discovered. It's actually, there are 3 planets around this star. Um,
Yeah. Which is
and
pretty impressive.
yeah, and so the sort of so-called metallicity, which is how much non hydrogen gaseous stuff is in the star, it's less than half of what is in the sun.
Yeah.
So it's a low, what they call low metallicity. It doesn't have, and so the surprising thing about it is we sort of think, well, stars had to go to work for a while, cooking the raw materials to make nice uh, protoplanetary disks around the next generation of stars, the so-called population 1 stars, so that then those disks could make planets because they'd have lots of solid or condensable things in the disks instead of just a bunch of gas like hydrogen and helium. They would have water vapor that could condense into droplets or ice crystals if they're far enough from the star, and those could stick together and grow and make big solid planets. But here we see one around a Metalpoor. Obviously, as Jim said, it's not population 3. There's still stuff there.
Yeah,
Right.
yeah. You said 10 plus or minus 3 billion years, but it can't possibly be plus 3 billion years, right? That would make it 13 billion years old. The universe is only 13.7 or something.
13
That would
point, yeah.
be that would make it really very very early. There's no way you'd make planets around those stars, but
Yeah.
Right. Well, this error bar is given to one significant figure. So it's 10 plus or minus 3, meaning it's not 10 plus or minus 2.
right.
So that's kind of, what are the big implications for that? It's always nice to sort of see planet formation being more robust and more prevalent in the universe than maybe we thought. And so this is an example of that. And it also means if there were, Earth-like solid planets forming around stars that formed earlier, this poses some Fermi paradox issues. Like, we've had guests on the show who suggested the resolution of the Fermi paradox is, well, we're just the first. We're the first on the scene. But if
That's
stars
worrisome.
that are twice as old as the sun were able to follow a similar path to what the Earth has done in terms of life, then that makes the first on the scene argument a little bit less viable. Of course, there's all sorts of other complicated things going on with life that's beyond just like, can you make a rocky planet? But
Right.
Yeah.
it's cool that there's this big uh, planet around a very old star in the galactic thick disk. So it
Yeah. They
increases
also
sort
talk
of,
a little bit about in the article about how it's going to be very, very hot. So it's interesting. It might be really interesting to study thermally, which is something that's a little bit hard to do sometimes, but they might be able to study it thermally because it's so hot.
Yeah. So this, yeah, that's right.
You
So
mean because it's giving off its own light because it's
Yep.
hot. So.
Yeah. Yeah. One of the cool things is if that like planets, you can look in the eye. There's some hypotheses that you can look in the IR, look in infrared for planets because they'll give off a lot of heat due to if they're heated up like that, compared to this sort of star that the central star. If you can like block that, you can detect these other planets a little bit better.
Yeah.
Yeah, as you
But
said, it's
yeah,
so close to the
really
star, it
close.
orbits in like 11 hours or something to go around the
Yeah.
star. That's how long
He's
its
zipping.
year is.
Did they say? I'm sure you guys may have said it already. How large the star is? How massive the star is? It is a sun type star.
This star, it has a V magnitude of 10.2, which tells us nothing.
No, I
Uh,
don't remember seeing how
its
big the star itself was.
its metallicity, as I said, is about zero point 0.4 of the sun's metallicity, but I'm not seeing right off the bat here what spectral type the star is. We'll have to
Yeah.
Because
track that
orbiting in
down.
11 hours around the sun would be catastrophically hot. But if you're orbiting that fast around a star that's much cooler, not as bad.
Yeah, I mean, it's a very warm star, but I don't know what type it is.
How warm? How warm? That's
Or,
the key.
yeah.
Yeah.
That is the
I mean,
key.
any star, if you're that close to it, you're going to be in trouble as long as it's not a brown dwarf or something.
Yeah.
But
So the innermost planet is, as Andy said, about 50% bigger than the Earth. There's a second planet that has its year is almost 11 days long, and it's 3 times larger than the Earth. Then that's the second planet. The third planet takes 16 days to orbit, and it is 2.3 times the size of the Earth. So that's a
Yeah, there's
fun.
potentially a fourth planet, I think.
I would imagine that there's potentially many more planets, right? Just this of course, as we've said many times, it's hard to detect ones that have much longer periods because you have to watch it for a really long time in order to see the periodic dimming because of.
Yeah, while we can't give the exact spectral type of the star, we know it's not much hotter than the sun because the sun won't last 10 billion years.
That's true.
And this star is potentially over 10 billion years old. So
Yeah.
it's probably a smaller, cooler star than the sun. Anyway, so there's lots of planets out there. So therefore, Star Trek is right. I think that's the
Great.
conclusion that we
Excellent.
can all draw from this. And that's really
great.
where I wanted to go with that whole story. Is this
Perfect.
proves Klingons and Romulans?
Is this a demon class planet?
It might be. I think
Whenever
it
we
might
talk
be.
about exoplanets, we always have to say like what Star Trek class they
class
are.
Y, demon class. Yeah.
Yeah.
Yeah. All right, you ready to take your stab at the launch stats? How many
Yeah.
Cubesats have been launched? Is it 1,357, 1,808, 2,293, or 2,611 as of the 1st of 2021?
Josh, if you wanted to get me, you should have spread those numbers out more, like way more orders of magnitude, because I wouldn't have even had a guess of the order of magnitude. I'm going to go with the highest number,
2,611. Okay, Addie, what do you say?
1808.
I got you both. It's only 1357.
Ooh, the lowest one.
Oh, okay.
The lowest number.
Okay.
Which year saw the most Cubesats launched? And how many?
2019.
It is 2017. There were
So
297,
smart.
297 launched that year. 2021 is forecast to shatter that record. However, the forecasts have been projecting every year to shatter every previous record, which has not actually happened since 2018.
So why are they not launching as many as they think they're going to launch?
That's a good question.
It's just taken a little bit longer to so there's supposed to have been a bunch of new launch vehicles for these types of things. And it's taken some of those longer to come online than they expected. But like if launcher 1 is successful this weekend, right? Then hopefully they'll be able to launch a bunch more. The Electron rockets are starting to put up a bunch and they're flying pretty reliably now. So I think like this year probably will. And I think there's 2 others that are going to probably have made flights recently and should make pretty good progress this year.
Yeah. How many are currently operational? And I'm giving you your choices: 210, 338, 561, or 804.
561.
800, whatever.
It
I'm
is
being optimistic.
800. Yeah. I also would have guessed 561.
Yeah, I guess what do they mean by operational?
I don't know that. There are 210 on orbit that are non-operational and 338 that have re-entered the Earth's
Okay.
atmosphere. And of that first number I gave you, about 100 of those were lost on launch. Um, the last question I'll give you is, what's the most common form factor for a CubeSat? We talked about 1U, 2U, 3U. There's also 6U, 12U, of these sort of, like, imagine taking these little or big Rubik's cubes or
Mm.
small Kleenex boxes and sort of assembling them Minecraft style into larger spacecraft. What is the most common configuration of CubeSat that has been launched? And that's your last chance to score points in this episode.
I'll let Addie go because
No, you go first. I went first the last time.
To you.
Oh. I think it's either 3U or 1U. I'm gonna go with 3U.
It is 3U. Almost half of the CubeSats are 3U. The
Yeah, I
1U,
mean,
only about
oh,
14% of
really?
CubeSats are 1U.
Wow.
Yeah.
Okay. I mean, the 3U is like the standard dispenser size. So like the
Dispenser? So what does that mean?
dispensers that you launch out of are like generally 3U. So you can either stack 3 1Us in there, you can put 1 3U, right?
Oh,
Surfsat was 2U. It launched with a spacecraft called Dave that was 1U. We launched together.
okay.
Yeah. So yeah, you don't take the CubeSat and just like stick it on the top of a rocket.
Doesn't have its own payload fairing.
It, it gets stuck inside some sort of dispenser, and there are a variety of those that are made that have these little channels that you slide the CubeSat into, and it has a spring. And when we delivered QPACE, we pushed it in against this big coiled up spring, and then a door came down and popped shut, and it's in there with 9 or other CubeSats, and when that gets delivered into orbit, that little spacecraft basically is going to open doors, and these things will get pushed out by these
So is this
springs.
all? I assume this is all like carefully calculated and everything. Like, I mean, I would think if you randomly sprung it off in random directions, you'd end up in crazy orbits that you didn't want, or end up crashing into the atmosphere.
Well, as you know, the orbital speed uh, is going to be about 7,000 meters per second. And the spring is going to be popping these things out at about 1 meter per second.
Okay.
So it's a tiny change to the overall orbital speed. We're sort of that. So whichever direction it's going, I'm sure they are thinking about that and everything, but
Yeah.
it's not making a huge change in what the orbit is.
But it does affect like the spacecraft spin and orientation and stuff like that. So like one of the complicated things when you're first trying to communicate with your spacecraft is it could be spinning weirdly for the first day or two, right? And it could like be really hard to make communications with it because its antenna is pointing in all weird directions. So
If
like
it's
our
spinning for the
spacecraft
first
actually has
day,
a
wouldn't
little
it?
magnet on it to help it align itself with the Earth.
Oh,
Yeah.
I was gonna say, how does it? Yeah, how does it? I mean, they don't have
A
like
lot of them are
thrusters
just
or anything
random.
like that in them,
Yeah,
so
they
they
don't have
can't.
propulsion.
So if they're
Some of them
if they're
do. Some of them have little propulsion things. Ours
oh,
don't, but some of them do. They have little gas propulsion
Mm,
thingies.
that have successfully flown?
I know that there are these like formation flying CubeSats that control how close they are to their buddy CubeSat using uh, some sort of thrust. Tiny, 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 tiny. But
Yeah, I mean, there's definitely lots of propulsion technology that's being developed for CubeSats. Not much of it has flown yet, though.
yeah,
And like,
and for
none of the
for
ones that are launched from the ISS have any sort of propulsion, basically, because that's not allowed yet.
and for orientation, some of them do have little flywheels inside them that they're powered by electricity from the solar panels that they can use to then rotate things around. But as Addie said, ours is using the power of the Earth's magnetic field, which brings
Huh,
us back to
magnets.
why
How do they
Addie
work?
chose electromagnetic field as her favorite field at the beginning.
Pretty powerful.
While it may have felt like the time from the first launch date of QPACE until the actual launch date, it was just another episode of Walkabout the Galaxy. Write us a review and send it to 100 Instagram influencers and let them do their thing. We'll give them 10% of our profit for every new follower that tags them. Be sure to follow us on Facebook and Instagram to get all our updates and check out our website at walkaboutthegalaxy.com. Subscribe to our YouTube channel where you can see most of our episodes, some of our bloopers, and all of our music videos. Catch up on old episodes wherever you get your podcasts. Follow us on Twitter
At walk_the_galaxy.
and ask us questions anywhere using hashtag AskWTG. Our theme music was composed by Richard Drusick. Thanks to our listeners in Italia and around the world. Stay safe. I'm Josh Caldwell.
I'm Maddie Dove.
And I'm Jim Cooney.
We're the AstroQuarks signing off until the next episode of Walkabout the Galaxy.
QPACE.